All right, I'll hit record now. All right, so we graphed it, magically appeared there. And now we have to find the limits. So let's find the limit as x goes to infinity. As x goes out to infinity, I'm walking this way towards infinity. What is y getting closer and closer to? 0. Okay? As x goes to infinity or negative infinity, they're going to be the same number as the horizontal asymptote. That should make sense. That's what the horizontal asymptote does. It makes your graph do something out at infinity. Also, same thing over here. I'm going out towards negative infinity. This graph is getting closer and closer. There's only one horizontal asymptote. So at both positive and negative sides, it's going to 0. Anybody have any questions on that? On that part? We're good with that part. Okay. Now let's look at what's happening at the asymptote. As x goes to -4 from the left, because there's a little negative there, -4 is right here. The left of -4, our graph is going down towards what? Negative infinity. All right, the next one is the limit as x goes to -4 from the right. So here's the right side of -4. We're going towards it. Our y values are increasing without bound up to positive infinity. Now the next question, you don't even need to look at your graph. You just look at what the left and right hand limits did for the next one. They're different. Yes, so they're different. They do not equal each other. Then that means that the limit at -4 does not exist, because left and right hand limits have to be exactly the same for it to exist there. 0, the limit at 0, you can use substitution, direct substitution, and just plug it in, right? You're finding the limit as x goes to 0 for 1 over x plus 4. Is there any problem with plugging 0 into that? Not at all. Not at all. So that would be 1/4. We've answered them all. And look how pretty that looks. All right. Any questions on that? We're pretty good? We feel a little bit better? Okay. Let's go to the next one, number 2. Number 2 is a different graph. So let's graph that one on our calculator. We'll go parentheses x plus 1. It's almost like the last one, huh? Well, not really. Divided by, you would go math num. That's where absolute value is found. X plus 4. We know there is going to be a problem at -4, right? -4, there's nothing there. All right. This one's a little different. Okay, it's not one of your typical rational functions. Okay. What you get is you do get a vertical asymptote at -4. 1, 2, 3, 4. Vertical asymptote at -4. But then you get 2 horizontal asymptotes. I don't know if you can see it. There's 2 ways you can see it. You can go to the table and follow x way out. 0.95, 0.96, 0.97. It looks like it's approaching 1. Okay? Then you can also go to the table and follow x the other way. -1.1, -1.09. It looks like it's going to -1. Okay? And I'll tell you why. So there's 2 asymptotes here. There's a horizontal asymptote at +1, and then there is another horizontal asymptote at -1. Now, do you see that absolute value? That's what's making it plus and minus 1. See how usually, like, take away the absolute value real quick, okay? What would be the horizontal asymptote? If you have x plus 1 over x plus 4, you'd have 1, right? Y equals 1. That would be your horizontal asymptote because the degrees are equal, it's leading coefficient. Now, because the absolute value is there, it means we do plus and minus 1. So they're both horizontal asymptotes. Let's write that over here. Y equals plus or minus 1. So our graph looks like this. It goes like, does it go? Yeah. It goes like this, and out towards this way is being affected by that asymptote. And if you graph the other half of it, out towards that way is being affected by the bottom asymptote. Horizontal asymptotes are weird, right? Because you can actually go through them. Like, they only affect parts of the graph. I went right through this asymptote right here. right there. I went right through it. You're not allowed to go through vertical asymptotes ever. That's a rule. But horizontal asymptotes can affect, one is affecting the right side, the other asymptote is affecting the left side. So now let's answer all their questions. You ready? So then what's the limit as x goes out to infinity? So jump on your graph, take your graph out towards infinity. What is y getting closer and closer to? Good.
Oh no, it's going to die.
I know. Oh man, I yelled at my kid this morning. It was dead when I got here. I had to borrow that from Miss Pfeiffer. Okay. The other way is as we're going out towards negative infinity, what's this going towards? -1. Okay? And look over here. I don't know if you can see this, but if I do infinity plus 1 over the absolute value of infinity, that's going to give me 1, right? Now, if I go out towards negative infinity and I do negative infinity over the absolute value of negative infinity, what does that give me? -1. Do you see that? Okay. All right, now let's look at the other one. The limit as x goes to -4 from the left, it's over here, is going down towards negative infinity. And then also -4 from the right is going down to negative infinity. So what is the limit at -4? Negative infinity, because they're equal to each other. What about what's the limit at 0? How about we just plug it in, right? Same as the last one, huh? 1/4. That's this right here, this dot right there, that's 1/4. And then what's the vertical asymptote? X equals, don't forget x equals, thank you, -4. All right, the next one is a little bit tricky. If you graph it on your calculator, and you graph parentheses x squared minus 16. Yeah, you can. Nope. Divide it by x plus 4. It's going to look like a simple line. Okay? This is not the graph of a line. We know what linear graphs equations look like. It's very similar to a line in that it does all the same things. Looks like this. But if you were to trace it or plug in -4, what happens? There's no y value. Nothing at -4. So 1, 2, 3, 4, there should be a hole in your graph at -4. Okay, and that should make sense to you because if you were to simplify it algebraically, like you said, this is x plus 4, x minus 4, and this is x plus 4 on the bottom. We still know that our domain is all reals except for -4. -4 cannot be in our graph because if you plug in -4, you get 0 in the denominator. But once you reduce, this is just the line y equals x minus 4, the hole in the graph. Okay, now let's do all the limits and stuff. Here we go. The limit as x goes to infinity. So as I go out this way, what are my y's going to? Infinity. Okay, as x gets bigger and bigger and bigger, so does y. As x gets smaller and smaller and smaller, going this way, what happens to y? Shoot. Hold on. Hello? Oh, hey, Karen, I'm sorry. Yeah, Jack's home today with his dad. He's sick. I should have called. Okay, all right, thanks. All right, bye. I knew it too, right, when I saw one of the Karens. Who knows? Okay. All right, here we go. Now, as x approaches -4, here's the one that some of you guys are going to miss, and it's sad. It's really sad. I'm going to cry. You're going to say it doesn't exist, and you're wrong. You're going to say D&E, D&E, D&E.
I didn't do that.
You didn't?
No.
No? It is.
Yeah.
Yes, good, okay. As you're going to, yes, as you're going to x from the left, what is y approaching? No, people don't see it, like they think it has to equal that value. But it's -8. That's right, good. 2 ways you can do that. One is you can go to your graph and you can plug in very close to -4. like negative 3.99999. And you'll get negative 7.99999. Or I like to do algebra, so I would plug it in right here where I've reduced. I got rid of the problem. Remember the problem area? And you plug in negative 4. You get negative 4 minus 4, and that would give you negative 8. So that's also the limit from the right side. It's also going towards negative 8. And then since they're equal, the limit at negative 4 does exist. Okay? People will say it doesn't exist just because there's a hole there. Doesn't mean it doesn't exist. Actually, holes, there will be a limit. And then at 0, what is it at 0? Negative 16 over 4, negative 4. Yep, and that's the y-intercept. That's right there. That's the y-intercept of our graph.
There's not any asymptotes.
None. None. Good. Ooh, I feel better for you. All right, let's move on. Backside. Yeah, what are the 4 types? Removable, okay. Infinite, jump. Good. As a class, you're really good.
Oscillating.
Oh, oscillating, yes. All right, removable, those are the holes in the graph. Okay. You wouldn't have to write holes. We're just reviewing, okay? There's also infinite. That would be when you have vertical asymptotes. Infinite. Then there's oscillating. Horizontal asymptotes, you can cross them. Vertical asymptotes, you can't. Oscillating, those are the ones that go back and forth. They look kind of interesting on your graph. And then, what's the other one? Jump.
Do we have to know oscillating for the test?
Yeah. So a jump would be something that jumps. There's a gap. There's a gap there. Different than a hole in the graph. It's a jump. Okay, here we go. Letter A, find the points of discontinuity. Then we're going to name the type of discontinuity, one of those 4 types that we just listed. Then if we're going to write the y value of the function that would make the function continuous. That only happens when we have a removable. That's only for holes in the graph, okay? If there's no hole in the graph, like look at number 5. Number 5 is not a removable. There's nothing to do, there's nothing to fill in there, okay? All right, so what is our problem here? What can x not be? 3, okay? So our point of discontinuity is going to happen at x equals 3. Now, you can graph this if you want to. What I like to do is I like to do this algebraically. Okay, we can do it both ways so that you can see both. And I would factor the numerator. The numerator factors is x minus 3, x plus 2. And we see that we can remove the x minus 3. Okay, so it is a removable discontinuity. And then part C is write the y value that would make it continuous. So let's take x equals 3 and plug it in. It's almost like you're taking the limit as x goes to 3 for f of x. What is it? 5. Perfect.
So all you're really doing is plugging in a?
Yes. You're plugging 3 in because what's happening at x equals 3, there's a hole in the graph, and we're trying to figure out what y value that would be to make it not a hole. And that would be by plugging it in to here, f of 3 plus 2 is 5. You can also graph it and go to the left and right and look at it that way too. I just like to do algebra so much. Okay, number 5, this one, I already know what the graph of number 5 looks like. You would probably need to graph it, and when you do graph it, you will see that it looks like this. Well, what's the problem? We know x can't be what? 0. Okay, so our problem is going to be at x equals 0, and at x equals 0, there's a hole in the graph right here, and our graph goes towards 1, and then negative 1, and it goes that way. Yes! That would be a, yeah?
There's no point at x.
No, there can't be. Yep, there can't because x cannot equal 0. So that would be a jump in the graph because of this gap there. right there. Sine x over x. Sometimes I look at that and I think, oh, that's going to oscillate. It actually doesn't. Sine of 1 over x does, but not this one. So you can graph this one. We've seen this one before. We took the limit of it on the last quiz at 0. All right, so here's the graph of it. Let's zoom in. We know what our problem is, right? Our problem is 0. X can't be 0.
Do we have to be radians?
No. Or then yes.
Is a whole? I mean,
Yeah. So x equals 0. X equals 0. And when you graph this, it goes like that, and it goes up to here. But your graph on your calculator, there's no y value at 0. So yeah, that would be removable. It is a hole in the graph, but its discontinuity is called removable. And then if we wanted to fill it in, okay, that you might need to look at your calculator. What's the limit as x is approaching 0 from both sides? 0.9999999. This side, 0.9999999. What do you think it is? No, it's 1. No, Trevor. All right, finally, number 7.
why does it have 2 ABs?
Because there's 2 points of discontinuity.
Are you going to find it be the same like this?
Yeah. Is that doable? X minus 2.
So x plus and minus?
Yes. So if you factor the denominator, factoring always helps you find the zeros. You will see that your points of discontinuity are -2 and +2. But they're very different from one another. You can graph this. One of them is an asymptote, and one of them is a hole in the graph. You can graph it if you need to. Graph the original. Don't graph after you've reduced it.
The 2 is the removable, right?
Yes, and you can see it algebraically. You don't even have to graph it. But if you are more of a visual, you want to graph it. Visionary, yep, you're so visionary. You can see there's an asymptote at x equals -2. There's a vertical asymptote. And then if I hit trace and plug in +2, there's no y value, so x equals 2, there's a hole in the graph, okay? So knowing that there's a vertical asymptote at -2 and a hole at +2, we can say what types of discontinuity these are. So at -2, that would be infinite because of the vertical asymptote. Did you get that, Jack? Good. I know, he needs to learn this because he's been not paying attention for the last week. Okay, and then part B is the 2. The 2 was removed. Do you see that? X equals 2. That would make that 0. That would be called removable. And there's only one part C. And part C only goes to the removable, to that one.
So it would just be 1 over x plus 2.
Yes, it would be.
Plug in 2.
Uh-huh.
1/4.
Perfect. So Lindsay was saying you do f of x equals 1 over x plus 2, because once you reduce these, you are left with a 1 up top. And then evaluate it at 2. Don't evaluate it at -2. You're going to get 1 over 0. That's not going to work, okay? Evaluate it at f of 2, and you get 1 over 2 plus 2, which is 1/4.
You're like 1/4.
I know, 1/4 showed up a lot here, yeah. Well, all of them had like -4 on the bottom.